Good day, everyone. So today we're going to go over Chapter 15 and um, just to sort of remind you of what we did in the past compared to what we're doing today, I have three examples here. So we looked at two variables before. Maybe we looked at uh, student hours, studying, all right, and then scoring an exam. And so notice that both of those variables are quantitative. When we're trying to figure out the relationship between two quantitative variables, what do we run? We run a regression analysis. Here, is there a difference in the genders regarding their average score in the math portion of the SAT? So notice we took a quantitative variable and we split it up. We had a categorical variable and its different levels, gender, male, female, all right? And we try to see if there's a relationship there. So what would we run there in that kind of situation? Two sample t-test. So again, two variables, but one was categorical and one was quantitative. Well, today we're going to look at a relationship like this. Is there a relationship between smoking and lung cancer? Notice both of those variables are what? Both of those variables are categorical. So we're trying to figure out if there's a relationship between two categorical variables. We're going to run the chi-square test of independence, and that's what we're going to run today. So the chi, that's not chi, it's chi-square test of independence. So just like before, we had a response variable, also known as the dependent. That's the one that we're trying to figure out why it's changing from person to person or thing to thing. We have the explanatory variable, also known as the independent variable. We test whether the response variable is at least partially explained by the explanatory. Nothing has changed there. All right, so how are we going to set up our data? Because this is a little different. It's categorical variable, right? And so we got categorical data. So how are we going to figure this out? Well, first of all, what we're going to do is we're going to create a contingency table, also known as a two-way table. And it displays two categorical variables. In the rows, list the categories of the explanatory variable. The columns list the categories of the response. So the response is going to go at the top. The explanatory is going to go on the side. So entries in the table are frequencies and is the intersection between a category of the response and the explanatory variable. So for example, let's say that we are looking at smoking and developing lung cancer. So we would all agree that lung cancer is associated with smoking, all right? But how do we know that? Well, we're going to build our way up to it. So let's pretend if you smoke, your chance of getting lung cancer is 30%. And if you didn't smoke, you only had a 1% chance of developing lung cancer. So maybe one of the reasons why you wouldn't smoke is because you see such a large association between what? Smoking and lung cancer. Now, how did you make that conclusion? Because there's such a difference between, well, my pen's not popping up. There we go. Uh, so uh, you probably made this association and you said, okay, well, there's such a large chance of getting lung cancer if you smoke, but a very small one if you don't smoke. By the way, these are made up numbers. But since these are very different from one another, this 30% versus the 1%, okay, you say, ooh, seems like there's an association. So when there is such a big difference in these percentages, uh, that is telling us that there's an association between the two variables. All right, so a large difference in these percentages is suggesting that developing lung cancer is associated or dependent on whether you smoke or not. So here's the background numbers. Let's start with the data. Okay, let's start with the data. So we have here, yes, we got 210 people that have lung cancer, and they were a smoker. And then we have 490 people that, yes, they smoke but don't have lung cancer. And then lung cancer, 7 people, and they're not a smoker. Okay. And then we have 688 that no and no. So the first thing I would do is if I had this data is I would start to come up with the subtotals here. So we had 700 smokers, 695 that didn't smoke, 217 that have lung cancer, 1,178 that don't have lung cancer. And be careful with this number. Either add up these two numbers or these two numbers. Don't add them. Don't add all four of them up because you will count everybody twice. So we had 1,395 total people in our sample. So let's see where the 30% came from. And we would ask something like this: what percentage of smokers develop lung cancer? And so we would start with the first row of the explanatory variable. So we would start with the smokers. And we would ask, okay, well, what percentage of these guys got this? All right, meaning, yes, they got lung cancer. And so there's 210 out of 700, or 30%. Well, guess what we're going to do next? We're going to go to the non-smokers, right? Do exactly the same thing. What percentage of non-smokers develop lung cancer? That would be 7 out of 695. It's roughly 1%. So that's where the numbers are coming from, all right? So notice here, the difference between 30% and 1% is probably large enough to say smoking and cancer are associated, or that lung cancer is dependent upon whether one smokes or not. So large difference in the row percentages suggests dependency, all right? So a large difference, okay? So difference suggests dependency between this variable and this variable, right? So let me go through another example. Let's say that we looked at gender, categorical, and graduating in 4 years, question mark, it's either a yes or no, all right? Two categorical variables, we want to see if they're related or not, meaning is there a difference in the graduation rates in 4 years? Again, just totally made up numbers. So we would ask the same types of questions. What percentage of females, all right, graduated in 4 years? So that would be what, 50 out of 400, or 1/8, or 12.5%, all right? Then we would go ahead and ask, okay, what about the males? What percentage of males graduated in 4 years? 75 out of 600, oh, 12.5%. And if you did that for the total, you would find the exactly same thing, 12.5%. So when all the row percentages are exactly the same, I mean exactly the same, this is an example of complete independence. So I have two examples here. They're pretty extreme. This one is showing complete independence. This is showing dependency. So when are we showing dependency? When the row percentages are really far apart. When are we showing complete independence? When the row percentages are exactly the same. We got to keep that in mind because this plays a huge part in the chi-square test of independence. All right, one last thing before we actually get into the particulars of the test. Homework might ask you to calculate a column percentage, but this will never ever assist us in figuring out if an association exists. So in other words, WebAssign might say, what percentage of the commuters are female? And so notice we aren't calculating row percentages, we're calculating a column percentage. What percentage of commuters? So when you say of commuters, we're talking about this column right now. And so, okay, we could figure it out. That would be 50 out of 110, or 45.5%. But this here is just seeing if you can calculate and understand the difference between the row percentage and the column percentage. But these column percentages will not assist us in figuring out if the two variables are dependent. It's the row percentages. So as long as you have the response up here and the explanatory here, row percentages, all right? All right, let's get into the particulars of the chi-square test of independence. So this test, this is testing whether there is a dependency or an association between two categorical variables. The test statistic has a chi-squared distribution with a certain amount of degrees of freedom. Now, warning here, unlike the t-distribution, the degrees of freedom is not, it's not based on sample size, and I'll we have to just develop the test a little bit, and I'll show you where the degrees of freedom are coming from. But the degrees of freedom for the chi-squared is not based on sample size. So let's just talk a little bit about the chi-squared distribution. Okay, so any chi-squared distribution starts at 0. So that's a little different than what we had before, because the standard normal, you could have negatives, right? You can have negative z-scores. Also the t was centered at 0. You can have negative t, all right? Here, chi-square starts at 0. The reason why is when you look into the formula for the chi-squared, you're going to see some squaring going on, all right? And so you can't have negatives. Chi-square distribution with small degrees of freedom is skewed greatly to the right. That's different too, because well, the binomial could be skewed, but certainly the standard normal and the t were perfectly symmetrical. The precise shape of the distribution depends on the degrees of freedom. That's kind of like the t. Remember, there's a family of t distributions. Well, there's a family of chi-square distributions. So here's a picture of 4 different chi-squares with their degrees of freedom. So notice highly skewed to the right with small degrees of freedom. Okay, and then as the degrees of freedom goes up, it gets to be what, more and more symmetrical. And actually, at degrees of freedom infinity, the chi-square turns into actually the standard normal. That's for more of a theoretical class. All right, the chi-square test of independence. The hypotheses are the following. Here's the good thing about the chi-square test of independence is that as long as you know that you're running it, that you're trying to figure out the association between 2 categorical variables, the null and the alternative basically don't change. The null hypothesis is going to be that the 2 variables are independent, not associated. Now, when we actually do a problem, we're actually going to fill in what the variables are. So this is a very generic statement here. We're going to actually fill in what the variables are when we actually do the test. In other words, here, if we're saying that the 2 variables are independent, that means the row percentages are going to be the same. And that's in the null. In the alternative, the 2 variables are dependent. They are associated, meaning the row percentages are very different from one another, or different enough to say that there's some sort of a dependency. So here's an example. We sample both male and female students at the University of Akron. We ask, where do you live, on or off campus? Test at the 5% significance level, whether gender and where a student resides are dependent, related, associated. Okay, so another way of thinking of the last line, test at the 5% significance level, well, there's a difference between gender and where they live. So let's say that this was our data, this was our sample, okay? So the first thing I would do is I would come up with the row percentages and, excuse me, the row subtotals and the column subtotals. So 200, 300, 160, 340. So we got a total sample size of 500. That's the very first thing I would do. You got to take great care in these numbers. If any number of these numbers are wrong, the whole test is going to be potentially wrong at that point. These numbers are extremely important in this test, these outer subtotal numbers. All right, here's the test statistic. It's a little different than what we're used to. So the chi, the symbol for chi is this guy right here. So it looks like this fancy X. Okay, so chi squared and test statistic, and it's equal to the summation of the observed minus the expected squared divided by the expected. So we haven't seen this stuff before, so I'll have to explain what these observed and expected are. A lot of times in a textbook, they'll eventually just kind of shrink it down to O's, meaning the observed, E's, meaning the expected, right? Okay, so where are the O's coming from? The O's are coming from the sample, the observed. You observe something, right? Where do you observe things from? You observe things from the sample. So those numbers right there, those are the observed, all right? So we have 4 observed. All right. All right. So the subtotals uh, are technically are not the observed. They're just subtotals of the observed. So we have 4 observed cell counts here. All right. What about the E's? Okay. The E's are calculated. Okay. The E's are calculated. The expected values are calculated. Some people call them the expected cell counts. Okay. But pretty much, excuse me, pretty much you'll hear the word expected in the phrase. All right. So the expected, there's a simple formula. You take the row total times column total and divide it by the total sample size. So here's our data again, and you're going to see where these subtotals come into play now. All right. So what we have to do is we have to go ahead and figure out then for this cell right here what its uh, corresponding expected value is. And then we have to figure out for this cell what its corresponding expected cell is, and then this one and this one. Okay. So let's start with this one right here. What do we got to do? We got to go to its row total, multiply it by its column total, and divide by what? Its total sample size. So what do you get? Let's see, you get 200 row total times column total of 160 divided by 500, you get 64. Okay, you get 64. So that is the corresponding expected cell count. Okay, this guy right here, the 64, goes along and is we have to eventually we're going to compare it to that number right there. Okay. Okay, how about this number right here? To figure out that, we go to its row total times its column total divided by its total sample size. So that would be 200. So I'm down here 200 times 340 divided by 500, we get 136. We go to the next one. 300 times 160 divided by 500. All right, I get 96. And finally, I go to this one over here. 300 times 340 divided by 500. What do we get? 204. 204. Okay, so now just to make sure that you did everything right, this test allows you to check your work. You know how in algebra that after you figure out maybe what x is, you can plug x back into the formula to make sure it works? Well, you can check basically your math here because if you notice here, if you took 64 and add it to 136, you get 200. This number right here has to match back to that number right there. If it doesn't, something went wrong. This number right here should match back to that number right there. If it doesn't, something went wrong. And for that matter, if you add up these two numbers, 160, they have to add up. 340, they have to add up. Okay, so if those do not add up and come back to the original values that we see for the subtotals in the observed, we did something wrong. Okay, we did some math wrong. Okay, so well, what is the definition of the expected values? What did we just do? This is actually one of the most important things to understand about the chi-square test of independence, all right, is this step right here. It's not actually, it's not even necessarily a step, it's an understanding of what is going on with the expected values. So let me remind you of something. For every hypothesis test, we temporarily assume the null is true so we can compare it to the sample. So what's in the null? Let's think about this. We have gender and where a student resides are independent. Okay, they're independent. So the expected values, this is the important wording right here. The expected values are what we would expect from the observed if the variables were completely independent, meaning the null was true. So here are the expected values, all right? The 64, the 96, the 136, and the 204. Those are the expected values, all right? And what I want to remind you of is this slide that I showed you before. Okay, this is where we had 12.5% for each one of these here. And what did we say? When all the row percentages are exactly the same, this is an example of complete independence. Okay, here are the expected cell counts again. All right, well, let's go figure out the row percentages based upon the expected. All right, so we would take 64, right? We would start with this guy right here, males. We would take 64 divided by what? 200. We get 32%. Then let's do that for this one. 136 divided by 200. We get what? 68. And let's go ahead and do that for males, females. And this one right here. What do we get? We get 32%. And we get 68%. So notice that what happened here, the expected cell counts are beginning to show you that they're all set to equal one another. 32%, 32%, 68, 68. Well, where in the heck did we get 32% and 68% from? Well, take a look at the total. The total is 160 divided by 500, and you get what? 32%. So if the total is 32%, then the test sets all of these at 32%. And that means if this is at 32%, that means that the total down here is going to be 68% and sets all of these to 68%. Okay, so that's what happened here. Is the expected cell counts are now basically I shouldn't say the expected cell counts, but for the expected cell counts, the row percentages are set to be exactly equal to one another. Meaning, this is our view, okay, of when things are completely independent. All right. So if our sample was showing these values are completely independent, then we should expect 64, 136, 96, 204 to be in the observed values. Okay. That's what we would expect the observed values to be if the variables were completely independent. So notice what the test statistic does. The very first thing in the numerator, what does it do? It compares the observed versus the expected. All right. So if they're completely equal to one another, this test stat turns out to be 0. All right. However, if they're really far apart, what's going to happen to the test statistic? So meaning the observed values are really far away from the expected. Okay, let's think about this. So if the O's are really far away from the E's, that will lead us to a high test statistic. High test stat leads to what? A small p-value, as we know. Low p-values will lead to rejecting the null and the conclusion that the variables are dependent. So the expected cell counts are what we would expect if things were independent. And the further away the observed are from them, the more it's showing that the variables are dependent. That's all. That's what the test is doing. Okay. So let's run through this. Step 1, state the hypotheses. So for our problem here, gender and where a student resides are independent. The alternative, gender and where a UA student resides are dependent. Step 2, verify the conditions/assumptions. So we need a random sample. And then we need all the expected E's, the E's to be greater than or equal to 5. And the reason why we do that is just to make sure that the sample size was large enough to support the table. And so what do I mean by that? Well, if you had a 2x2 table, meaning you had 2 levels of the explanatory and 2 levels of the response, you wouldn't need as large of a sample size there compared to, say, a table that had 5 levels of the explanatory variable and 5 levels of the response. Because now you, instead of having 4 cells, you got 25 cells. All right. So this is just making sure, okay, that you have a large enough sample size to support the table that you have created. All right. So here's our expected cell counts, and they're all greater than or equal to 5. Okay. So we have what we needed there. All right. So now, the way I would do this on a piece of paper, if I was doing this by hand, which you should be doing, is that, I gotta get my pen back out. is that I would go ahead and first start with the observed, which will be given to you in the problem. I would create the subtotals and the total sample size. Then I would create another table, a duplicate of this one, other than that they're going to have the expected cell counts. And so I would go ahead and figure out the expected cell counts, make sure these match up to subtotals, okay? And now you can go ahead and do the test statistic, all right? And remember, we're just going to follow the order of operations, all right? So we're going to set up a table that just simply follows the order of operations. So what does it say to do? It says take your O's minus the E's and square, that's the first thing you got to do. Is you got to take each one of your O's, subtract off its corresponding E, because that's in parentheses. Then we're going to have to do square all of them. And then we're going to have to take those numbers and divide by the expected cell counts. And then in the end, what do we add, right? Add. That's usually what happens with the test statistic, okay? So notice I set up a table that follows that exact order of operation. We have our O's, we have our E's, O's minus the E's, then they're squared, and then divide by E, all right? So we start with the first one. We would start with, say, 70 as their first O. So we have 70 for our first O. Then its corresponding E is 64. We subtract off the 2, we get 6. We square them, we get 36. So we get 36 divided by the 64, because we come back to this number here, we get 0.563. And we would do that for each one. So then we would go to the 90. You can go to the 130 if you wish. It doesn't really matter. You can go to 90 next. But if you go to the 90 next, then you got to compare it to the 96 here. Okay, if you go to the 130, you got to compare that to the 136. So I went to the 90. So 90 minus 96, that's a negative 6. Squared, 36. 36 divided by the 96 is 0.375. So I do that for the 130, okay? And then I also do that for the 210. So notice something interesting that happens here. Whenever you have a 2 by 2 table, all right, if you did all the calculations correct, if you have a 2 by 2 table, what's going to happen is that for the O's minus the E's, you're going to get 2 negatives and 2 positives of the same exact number, all right? And so notice you got 2 positive 6s and 2 negative 6s. No matter how large the table is, though, so that's not going to happen, say, for a 3 by 2 table or a 3 by 3 table or a 4 by 5 table or whatever, okay? But what I can guarantee you is that this column will always add up to 0 if you did everything correctly, okay? So that'll always add up to 0. Make sure that you take away the negative signs here, all right? Remember the chi-squared has to be positive, all right? So all positive numbers here. And what's our last step to actually calculating the chi-squared is that we have to add up those numbers now. So you have to add up these guys right here, and it turns out to be 1.379, all right? That is our test statistic. Do not square this value. This is just a symbol here, the chi-squared, all right? The squaring has already happened. It happened right here, okay? Don't take the sum and square it, okay? Just sum it, and that's your test stat, okay? So we got to then calculate the p-value, and in order to calculate the p-value, we're going to need degrees of freedom. And so the degrees of freedom for the chi-squared is not a function of the sample size, like I said before. All right, and what we got to do is we got to take the number of rows in our table, in our original table, -1, times the number of columns, -1. And so a lot of textbooks would just say that's R -1 times C -1. So what we're talking about here is that, okay? So basically ignoring the subtotals, all right, and just looking at how many levels did we have for the explanatory and how many levels did we have for the response, all right? And so we had 2 rows, 2 columns. When you throw that into the formula, you got 2 minus 1 times 2 minus 1, you get 1 big degree of freedom when you have a 2 by 2 table. That's it, all right? So we got 1 degree of freedom, And let's see here. We had a test statistic of 1.379. All right, so I have to get out of this and get into StatCrunch. Let's go ahead and do that because we have to look this up. I already gave you what the p-value is here, but I'll show you how to do that. So going over to StatCrunch. So what we got to do is we got to go to Stat, Calculators, and down here is the chi-squared. It defaults to 10 degrees of freedom, all right? And this kind of drives me nuts. Honestly, it probably should default to greater than, because the chi-squared test of independence, and actually most chi-square tests are always right-tailed. They're always right-tailed, okay? And so because everything got squared and got pushed to the right on the number line, all right? So everything is a right-tailed test. And so we need a greater than sign here. We need 1 degree of freedom, and we got to look up 1.379. So 1.379. Compute, and there's our test stat of 0.2403. And it gives you this ugly picture of 1 degree of freedom, okay? And so it's taken up a lot of the probability distribution underneath that curve, right? So 0.2403. There's our answer for the p-value anyways, okay? Okay, so I gotta let my computer catch up here, get back into the presentation. So when you do your homework and WebAssign asks for a p-value, all right, head over to the StatCrunch to figure that out. All right, conclusion. P-value is 0.2403. That's greater than 0.05, our significance level in the test. So do not reject the null. And just to remind you what was in the null and the alternative. So we do not have strong evidence at the 5% significance level that gender and where all UA students reside are dependent. So remember, we're not going to say that that for sure they're independent. We would have to have basically a test statistic of 0 in that situation. And so we're not going to have that ever. And so we're not going to say that these variables are independent. We're just going to say that we don't have enough evidence to say that they are dependent. Okay. One more. We'll go through this quicker. Okay. We'll go through this a lot more quickly since we already went through the particulars here. So in a 2014 random sample of US adults, so this actually happened, people were asked whether they believed in heaven. Along with this question, they were also asked what religious affiliation did they belong. So people were either classified as either Christian, non-Christian, or no particular religious affiliation. Tested the 5% significance level, whether for all U.S. adults that belief in heaven is dependent upon religious affiliation. Okay. And so notice here we have two variables, right? We have religious affiliation and do they believe in heaven? Okay. Two categorical variables. Here was the data. I'm going to put here as the response, okay? I'm going to put the response here as did they believe in heaven or not, and then their religious affiliation as the explanatory. To me, that only makes sense. And I would go ahead and calculate the subtotals here. So I got 275, 80, 45, 289, 111, and a total sample size of 400. All right, there's our test stat. And so we have our O's, we have our observed. Remember, the observed will be these numbers in here. So we actually have 6 observed. All right, I'm supposed to include the 17 there. Now we have to figure out the expected cell counts, but remember, those are good. What are we going to use to figure those out? We need the subtotals here, all right, and then the total sample size. So I went ahead and did that really quick, okay, for you. So again, for this guy right here, we would take 275 multiplied by 289, divide by 500, excuse me, 400, and notice it doesn't come out to a nice number like it did before. And I would expect that from a real sample, all right? And then this guy right here, we would take 275, multiply it by 111, divide by 400, and I got that. So notice when you add those up, you do come back to 275, and if you did that for all of them, you come back to the subtotals, all right? So again, if you forgot what we had to do, you might have to go back a couple of slides, all right? I thought I would probably bore you, though, if I showed you all the math again. So we got our O's, we got our E's. I think we're going to actually run through the tests. So state the hypotheses. Believe in heaven and religious affiliation are independent for all U.S. adults. And then dependent for the alternative. Hopefully I didn't go too fast there. But it doesn't change, right? It doesn't change. That's why I kind of went through it quickly. So verify the conditions, random sample. Hopefully that was truly done. And then all the expected E's are greater than or equal to 5. Are they all greater than or equal to 5? Are all the E's greater than or equal to 5? Yep. Check mark. All right. That means we can use the test statistic that I showed you before. And here's all the gory math. And yes, it gets a little messy because we have 4 decimal places here. Okay. But here's the O's minus the E's squared, right, divided by the E's, and we would have to take this column right here, all right, add them up. I came up with a whopping 73.7302. That's a very large test statistic with only a 3 by 2 table. Again, notice here with the O's minus the E's, if you add up this column here, it's going to add up to 0, and it does. So that's another good check, right? It's another good check. And remember, when you get to this column right here, only positive numbers, all right? And this is what each cell contributed to the test statistic. All right, degrees of freedom. For here, we had how many rows did we have? We had 3. How many columns? 2, right? And so we have 2 degrees of freedom here. I'll assume that you'll be able to do this in StatCrunch, okay? And, oh, I went too fast. The p-value, that's the actual p-value here. I think we have a pretty conclusive decision to make here, all right? I don't think there's any doubt. So that's truly the p-value, okay? So the conclusion, p-value is extremely small, less than alpha. We'll reject the null, all right? Here's the null again, here's the alternative. So we have strong statistical significant evidence at the 5% significance level that believing in heaven and religious affiliation are dependent for U.S. adults, for all U.S. adults. And so we said reject this, we think that, and there we go, okay? So why did it, so in other words, there's a big difference between the groups and their beliefs in heaven. Big difference, huge difference. So let's see why really quick. So here's the actual data, right? This is the observed. And so let's look at the row percentages for Christians. So I took 234 and divided by 275. Came out with, I rounded just to the whole percentage, 85%. Look at the row percentage for the non-Christians. It turned out to be 47.5%. And then the row percentage for no affiliation turned out to be 37.8%. So notice how big of a difference there are between these groups. Bigger the difference, bigger the separation, the bigger the test stat, the smaller the p-value. A lot of evidence to suggest that these variables are dependent upon one another, meaning religious affiliation and belief in heaven, right? And look at the row percentage for the total. So we had huge difference, okay, in the no affiliation versus the total. Pretty big difference in the non-Christians. And then the Christians in the U.S., they sort of dominate. And so the random sample produced a lot more Christians than anybody. And so their percentage is going to be closest to the total just because of that fact. All right. So big difference leads to big test statistics, and that's going to lead us to small p-values and rejecting the null and saying that the variables are dependent. All right. I think that takes us to the end of the presentation. Thank you for your time.